So this is the fourth lecture on this talk about the series of talks about singular points of complete vector fields, and I would like to address now the birational point of view. So the idea behind this birational point of view is that so we saw before that we can talk about, for example, in surfaces, we could talk about normal forms for semi-complete vector fields. We saw some normal forms about the saddle nodes or about the vector fields that have trivial first jet and isolated singularities. We did not talk about normal forms for singularities of vector fields that are not isolated. And we did not talk about, we talked about manifolds, but we could also do the same discussion for analytic spaces, for singular points of analytic spaces. And the birational point of view will be a good one to study these singular points of analytic spaces, as well as non-isolated singularities of vector fields. And the thing is that when you have a vector field and you have a zero of your vector field, you can blow it up and you will still have a holomorphic vector field. If you blow up a point that is a regular point of a vector field, you will get a meromorphic vector field. But if you do it carefully, with a purpose, you will find holomorphic vector fields. And in general, the vector field you will obtain will be simpler above in the resolution, and you will translate. You will find a simpler situation locally, probably a more complicated situation globally. But that's what we will have to talk about. Okay, so in order to discuss this birational point of view, again, I will only discuss surfaces, dimension 2. I will not discuss, at the end, I probably say something about what happens in higher dimensions. And this birational point of view needs definition of what a reduced singularity of a vector field is. So I will suppose that you know what a reduced singularity of a foliation is. This is the theorem of Seidenberg. I've proved that in surfaces. So this is surfaces. I'm not saying, but I will only talk about surfaces. Okay, so a reduced vector field, again, I told you in the last lecture that a vector field is, in some sense, a foliation and a divisor curve with multiplicity. So a reduced vector field will be, on one hand, that a foliation that is reduced in Seidenberg sense, and some notion of compatibility between the curve and the foliation. These sort of things have been considered by many authors. Cano and Cerveau have talked about this compatibility between foliations and divisors in the resolution of singularities. I will give you one definition that works well. So one possible thing of saying that the curve of zeros is adapted to the foliation is saying that when you consider a non-singular point of the foliation, then your curve of zeros should be transverse to it. Okay, so that at this point, the union of the curve of zeros and the separatrix is a normal crossing. Now, the other situation is the one where your foliation is has a singular point, and then in this case, I already have a normal crossing of two curves, so the definition implies that the curve of zeros should be one of these separatrices. So if the union of the curve and zeros and the leaf of f through p, if p is not a singular point, or the union of the separatrices together with the curves is a curve with normal crossings. Okay, and you can get to, after using Seidenberg's result, you can see that if you have a vector field, then and the point of this vector field, singular point, the point where the vector field vanishes, if you take sufficiently many blow-ups, then you will find a vector field that is reduced in this sense. Okay, so we have a notion of what are reduced vector fields. Is essentially Seidenberg's theorem tells us that we can have reduced vector fields. And the thing is that we can give normal forms in a very concrete way, a very concrete list of normal forms for reduced vector fields on semi-complete vector fields. Okay, so I have here normal forms. So if I have a surface and I have a reduced holomorphic vector fields, and this vector field is semi-complete, of course, I forgot to tell you, but it's true that if I blow up a vector field, a semi-complete vector field, I take a zero of a vector field, semi-complete vector field, and I blow it up, then I will find another semi-complete vector field. So it really makes sense to talk about this by rational binomorphic theory of semi-complete vector fields. And if I have a vector, and then we have, as I show you here, a list of normal forms. They are very, very simple. So we have the following possibilities for the vector field. The first one is that your vector field has a non-degenerate isolated singularity. So this is the first possibility. So these we knew. So this is, of course, reduced. And here we have only one singular point and the vector field. So there are this is no curve of zeros. The other one is, and the other ones, so the second one you see here is what you call, is the saddle node. And in this case, we will also have, I will not draw the saddle node, but here we also have an isolated singularity. So if you see that your foliation is a saddle node, and you see a curve of zeros passing through the saddle node, then you are not in a semi-complete vector fields. The only way in which saddle nodes may appear are as isolated singularities. Okay, so these are the isolated singularities, and the remaining ones are non-isolated singularities. You see, for example, they have as foliations, the first two have non-trivial linear parts. Actually, the first one has also a first integral, and in the last one, you will find what we said before. The last ones concern points which are not singular points for the foliation, and where the curves of zeros have this form. Say, I have one here, a leaf of the foliation, and another one transmits. Okay, so this is the last situation, and these are the only possibilities, and these normal forms. These are the only things that can happen up to multiplication by a non-vanishing holomorphic function. So as you see, we have a very reduced list of normal forms. So putting this together with the classification of the singularities of the classification of the affine structures with singularities on compact surfaces that we discussed, we can say, for example, if I have a singularity, if I have a singular surface with a semi-complete vector field, and then I can resolve the surface, the vector field will lift to a vector field. If I started with a semi-complete vector field, I will start with a semi-complete vector field. And afterwards, I solve the surface, I can reduce the singularities of the vector field. So what I have in the end is a bunch of curves that will map to a singular point. And I reduce vector field above here. So if these curves are invariant by the foliation, then necessarily they belong to the list that I gave you in the previous lecture. They are rational and elliptic, and they have a very definite geometry along this curve if they are invariant by the foliation. And when two of them intersect, then the local model of the vector fields along this intersection belongs necessarily to this list. So we have in principle a lot of information. And of course, we know a lot of things about foliations in dimension 2. And we have the Camacho-Sad index theorem that tells us that there's a topological counterpart that can be read from the local invariance of the foliations and the vector fields. We have a lot of information about these. So, and we have many settings where we can really take the combinatorics that go with this description to the end. So let me give you one example of this. This will be one example that I already told you about. So suppose you have a two-dimensional normal irreducible Stein space B. Okay, so this is Stein, so this you have to think of it as a very complete Stein space. And I have a complete vector field, and I have P, a singular point of the space that's an isolated zero of my vector field. So the vector field possibly has a curve of zeros, maybe invariant, maybe not, but these curve of zeros do not accumulate to the singular point. So the theorem says that we have two situations. The first one is that P is a weighted homogeneous singularity. I will give you an example in a minute. And the other one is that P is a cyclic quotient, or Herzog-Jung singularity. So let me give you, before I would like to give you a proof of the theorem. Probably, okay, I don't need the full list of normal forms that I just showed you, but I will tell you this as well. Let me give you first, I would like to give you a proof of the theorem, but first we'll give you two examples. The first example is a singularity that is called the E8 singularity. This will be the first. Okay. Let me give you an example of the second situation. So this V is called the E8 singularity. It's an algebraic affine surface in C3. It has a singular point at 0. And it is a quasi-homogeneous one. If you give X the weight 15, Y the weight 10, and Z the weight 6, you have a homogeneous polynomial of degree 30. And as every homogeneous or quasi-homogeneous, it comes with weighted homothéties that preserve it. So in this case, I have this vector field, this linear vector field, which acts by multiplying by the weights. The weights are not the ones I told you about, but you can figure out what the weights are. And then, oh yes, they are the weights. The weights are what I told you about. So I have a weighted homothéty that preserves the vector field, and this gives me an example of a Stein surface with a singular point and a vector field, a complete one, having an isolated singularity. Okay, so this is the first example. So this is an example of this situation, weighted homogeneous singularity. And for the other one, let me tell you one example. So I have here two examples of complete vector fields in C2. The second one is with lambda and mu non-zero complex numbers. And these are complete. This is a complete vector field in C2. The first one is also a complete vector field in C2, is in the Dulac normal form. The second one has two invariant curves, z equals 0 and mu and w equals 0. The first one only has one invariant curve, the curve z equals 0. Okay, so all these vector fields, in this case, m is an integer. So all these curves give you complete vector fields. And let me give you one group of cyclic transformations, cyclic linear transformations of C2 that will fix the origin and that will preserve these two vector fields. So choose an nth root of unity omega, and let it be a prime n prime with m, and just multiply your variables z and w by these powers of omega. So you can see that this preserves your vector fields, both of them, and in the quotient, when you take the quotient, you will find this. You will find a singular point coming from 0. All the other points will be smooth points, and the surface you get is an affine algebraic surface. It can be properly embedded in C2. In particular, it is a Stein surface. So this gives me examples of the second situation in my statement. Cyclic quotient of, or Hirzebruch-Jung singularity. This is an example of this one. Okay, so the theorem says that that's all there is. If you have a Stein surface and the singular point and the curve of zeros does not accumulate, then it is one of these ones. And for this second, I told you that under this cyclic quotient, I have a singularity, and this singularity can be described. It has a resolution that's very easy to describe, and that's what we will use in order to prove the theorem. So you can write the quotient n over m as in form of these special continued fraction. This is not the standard continued fraction. There's some minus here, and I am also supposing that ki is greater or equal than 2. But n over m, all the rationals have expressions of in this sort of what I call sometimes Hirzebruch continued fractions. So let me tell you what the resolution looks like. So I have the singular point, and when I blow up the singular point, I will find a chain of rational curves. You know, sometimes you put points for each component, and you join points that intersect. So the resolution will be given by S rational curves that form a line in this, like the first one intersects the second one, the second intersects the first, and the third one, and so on. And the self-intersections of these rational curves would be just minus ki. So this is what the resolution of the singular point looks like. And in fact, in this case, the combinatorics of the resolutions gives you the whole singularity. So if you see a chain of curves, of rational curves in a surface, and they have these self-intersections, then when you contract these two points, you have something that's analytically equivalent to the Hirzebruch-Jung singularity A and M. Okay, so from N and M, you get the chi-i's, and from the chi-i's through this continued fractions, you will get N over M. Okay, this is more information. Okay, so let me go to the proof of the theorem. Okay, and I would suppose for this proof that X has at least one separatrix. So this is not a hypothesis of the theorem, and is one of the interesting parts of the theorem is that under the hypothesis that the surface is a Stein one, you necessarily have one separatrix. I will not tell you more about this, but I will just, for this sketch of proof, I will just assume it. Okay, so I have my vector field and I have one separatrix. So I have one curve that goes to the singular point. It's not a curve of zeros. And we already saw in the first lecture that along the curve, the vector field is either lambda z d over dz or z squared d over dz. These are the only two possibilities. But we also saw that if in this case, this curve should complete, if I am in a complete vector field, this piece of orbit given by the separatrix should complete to a P1. This is what we saw in the first lecture. But we are in a Stein space, so this cannot happen. Because Stein spaces do not contain P1s. Okay, so you are in the, you have at least one separatrix, and you know for sure that the vector field along the separatrix looks like this. Okay, and there are two cases. So either you have infinitely many separatrices, infinitely many, or finitely many, and these two cases distinguish the two possibilities that I showed you in the first slide. So remember the weighted homothéties, if you take an orbit, it will go to the origin, and it will give you, from any point, we'll have a separatrix going through a singular point. And in the second one, I showed you that either the vector field had either one or two singularities, two separatrices, and in fact, these are the only ones. Okay, so if you have infinitely many singularities, then after you consider the resolution of singularities, you will find one curve, a curve of poles, and you will see that the vector field will be transverse to it. So the purple line is a component of the curve of zeros and poles. And along each one of these curves, you will find either a vector field of the form lambda z, or maybe a curve of zeros, like this. So in any case, along each one of in these curves that are not in the curve of that are not like the pink one, which if the vector field is not identically zero along this curve, you have this eigenvalue of the vector field, this lambda. And this lambda gives you a function along this purple component. It vanishes in the curves where the vector field, along which the vector field vanishes identically. So you have this lambda gives you a function, a holomorphic function along this compact curve. So this is compact. So this function is constant. So you do not have, in fact, you do not have these pink curves. And lambda is the same for all the curves. So in fact, along all these curves, you have the same curve, lambda. So you have a period for the action. So the period is the same as the period of the vector field lambda z. 2I pi over lambda is a period. So this leads you to the weighted homothéties. So we have an action of C star and a component where many separatrices lead to. So you can go to here, and you can from here you have all the description given by Orlik and Bachreich about these sort of singularities. Okay, so and also I started with the hypothesis that the surface was a Stein one. So if I am in the situation of infinitely many singularities, then the theorem of Camacho, Movazati, and Scamdo tells you that actually we're not in the most general Stein case. So it tells us that we're actually in the affine algebraic case. Okay, so this case is very well understood, the case of infinitely many singularities. And now for the case of finitely many singularities, I know that I have one separatrix, and it leads to one point that will belong to some divisor. Okay, and the vector field does not vanish along this curve. The vector field is actually in the form lambda z d over dc along this curve. So it has one point. And if we look at the list of singularities, two things may happen. So either the vector field, let me draw it like this. Either the vector field is a saddle node, the singularity is a saddle node, we put Sn. So saddle node. Or a regular one. Okay, so in the case of the saddle node, I saw before, we have one singularity, one curve along which the vector field is lambda z. And in the other one, we have a curve like c squared d over dz. So in this case, we know that this curve cannot be an ambient. This orbit should complete itself within the ambient manifold. Here I am talking about, I am making this argument in the resolution of the singularities. So we know that this curve P1 that we still have here cannot be part of the ambient manifold, so it should be part of the, it should be one of the curves that get blown down when I take the resolution. So in the other case, I have a regular, this can happen, okay? In the other case, I will find a regular point. So I will find a curve with a vector field that has one singular point, lambda z, and it should have another one which has the same form. So if the vector field is lambda z here, at the other singular point should be, this would be a rational curve, should be minus lambda z. So at this point, I'm in exactly the same situation I was before. I have a curve of the form lambda z coming here. So there are two possibilities. Either there is some other rational curve and another curve lambda z, or there is a saddle node at the end of this curve. So I start with the separatrix comes in, and then I have either the curve has no other singularity, either I have a saddle node and the curve has no other singularity, and then the divisor should be it, because I have no other way to complete the divisor, or else I have another rational curve, and another rational curve, and another rational curve, and another rational curve, and at the end, I may have either a saddle node or another one of these curves, and this curve belongs to the ambient manifold. So in any case, what I find is that I have finitely many, I have a chain of rational curves, just like in the resolution of the cyclic quotient singularity A and M, and probably I have one curve. All these become, because all these come from some negative, something that can be collapsed to a point. The self-intersections are negative, and if you have something with self-intersection -1, you can just blow it down. It doesn't change anything. You can blow down all the -1s. The description will remain the same. So at the end, I will find a chain of curves that will be exactly like the cyclic quotient singularity. So they will be, because that's the property of the cyclic quotient singularities, they will be cyclic quotients. So they come into flavors, either have one or two singularities, and they correspond essentially to the one or two separatrices of the vector fields that I was talking to you about when I showed you the examples. So in this case, the case where we have finitely many singularities, we do not know what the global situation is. in the infinitely many, in the case where there are infinitely many situations, we know that the singular point that we have is in fact the only singular point of the space. But in this case, we do not know. We do not know if the basin of attraction is the whole space or not. We do not know many things. Okay, so this is the sort of things that you can do when you put together on one hand, the resolution of vector fields, together with the normal forms for semi-complete vector fields, together with information on the geometry, on the affine geometry on the exceptional devices. This is one situation where the combinatorics can be pushed to the limit. Another one concerns compact complex surfaces. I will not tell you much about it, but in the year 2000, Lusky, Oljeklaus, and Thoma completed the classification of compact complex surfaces that are holomorphic vector fields. They used for this the work of Gis and Rebello. And with this combinatorics of semi-complete vector fields, that is actually all this, I know if I said it, these combinatorics and these normal forms for complete vector fields appear in an article with Giulio Rebello. So if you take together these combinatorics, you can, in a very straightforward way, just in the same spirit as I showed you, give this very simple statement for compact complex surfaces without going into the whole Kodaira and Rick's classification. If you have a minimal compact complex surface and a holomorphic vector field on S, well, under this situation, your vector field will be a complete one, so it can be studied by the tools I have described you. So you can see this. This implies, if you do the combinatorics, that either X has no zeros, or the flow factors through an action of C star, or your vector field has a first integral, or, and here comes the interesting parts, X is a very special surface, a Kato surface, and in fact, it's interesting that all these combinatorics allow you to distinguish these Kato surfaces in a very efficient way. These come from the non-Keller side of the surface world, non-algebraic, and or there is a divisor of elliptic fiber type invariant by X. There is some sort of degenerate elliptic curve of vanishing self-intersection, and in this case, last case, well, so this could be used to lead to a classification. I think this is a very cheap way to do it if you want to classify the surfaces that have vector fields. So these this divisors of elliptic fiber types in the algebraic setting through the work of Brunella will lead to fibrations in the algebraic case. And in the non-algebraic or non-Keller will lead you, for example, to Hopf surfaces or Enoki surfaces, all of them. So, so I won't tell you much about this statement. This statement really, except for the fact of the Kato surfaces, really follows by doing these combinatorics. But I just want to show you that these local methods allow you to go from Stein surfaces to compact surfaces and so on. Okay, so I am approaching the end of this series of lectures, and let me just finish with some questions. So I did not mention dimension 3. Mainly, we know little things. Well, we know in dimension 3 we have many examples of semi-complete vector fields. The resolution of singularities in dimension 3, you know, we have these theorems of resolution of singularities foliation by curves by Panazzolo and McQuillan on one hand, and Cano, Roche, Spivakowski on the other one. And in fact, we do not need the full strength of these theorems, as Rebello and Reis have shown. have a resolution of singularities. We have many examples of semi-complete vector fields in C3, polynomial ones. We have a very detailed study for saddle nodes done by Elena Reis. But still, there's a lot of things that we don't know in dimension 3. So I don't know what can be said about complete polynomial vector fields in C3. That we don't really know. We know, we can say a lot of things if they have a first integral, but if they don't have a first integral, then we really don't know much about these vector fields. But surely all these local methods can be useful. So we do not know. That's one question. Another question, we do not know much about complete holomorphic vector fields in C2. If your vector fields are polynomial, then Brunella gives you normal forms. That's everything you want to know about. So you can say everything in the polynomial setting. Brunella gives normal forms up to polynomial automorphisms. But for general complete holomorphic vector fields in C2, we do not know anything. So probably the question is, how can you talk about what happens at infinity in these vector fields? And just one more question. Remember, in my first lecture, I told you all the things we could do with the separatrix theorem, that as a consequence of it, we know that if I have a singular point of vector field in dimension 2, and if the singularity is isolated, then the second jet, using the fact that this vector field has a singularity, the second jet must be non-trivial. So we do not know what happens in dimension 3. We know that germs of vector fields in dimension 3 do not have, in general, separatrices, but maybe complete ones do. Maybe semi-complete ones do. We don't know it. We do not know it. So if I have a germ of semi-complete vector field in the origin of 0 in C3 with an isolated singularity, does it have a separatrix? We do not know. Can its second jet be trivial? Of course, if it does have a separatrix, then its second jet is not trivial, but maybe there's another way to show that the second jet cannot be trivial, or more generally, tell me a precise way in which this germ of vector field cannot be too degenerate. Okay, so there are many more questions, and just let me finish with some references. So many of the things as I said, were part of the early work of Giulio Rebello in surfaces. So over the time, we have come to better understand the many things. So we can now say things in a better way, I think, than we did some years ago. So we have these articles, and you can consult. Maybe the introductions can work as an introduction to the subject. So many of the things I told you in these two last lectures can be read in these articles. Okay, so I thank you very much. If you have reached the end of this fourth lecture, I thank you for your patience, and see you next time. I hope to see you once live in another location. Thank you very much.